Okay, next we have to represent minus 16 into its equivalence binary number using 2's complement. Okay, so what we are going to do, okay, so I can use this shorter method to give the powers and find out the value of 1. So I have used this table 1 2 4 8 16, and I need 16, so I will write here 1 and the rest will be 0 because I don't need to add them. Okay, so for 16 I have 1 and for 0, but I need to represent its negative 16. So what I can do, I can take its 1's complement over here, so it will be 1 1 1 1 and 0, and then I will be adding plus 1 over here, so this will be 1 plus 1 0, carry. Again the same process we did in the previous question, we are going to repeat this, and this 1 and 1 over here. Okay, so now this is the final answer for minus 16. Okay, you can see over here 16 is also same like minus 16, both have the same value. This is a constant, it can also happen, but you can also recheck whether this is equivalent to minus 16 or not. So what can we do? Remember, as I told you, that you are representing a negative value using 2's complement. So when you are giving power, you can what power you can give to this negative number? This can be 1, this is 2, this is 4, this is 8, and the last power will be written with minus 16, right? So I'm not going to add these number because they have 0, so I will only consider this value. So what is the value above 1? It is minus 16, right? So this is equivalent to minus 16. Okay, next question is, you have to represent minus 1 using 2's complement. This is also very simple. Minus 1, simple. Suppose what can be the value of minus 1 in binary? You can write it, suppose I'm using 2 bits, so it can be written as, the only one can be written as 0 1. Okay, for negative value, what we'll do, we will find out its 1's complement. So for the value of 1, it will be 0, it will be 1, and then I will be adding 1 in it, and it will be becoming, just leave this one and add these values. This is 1 and this is 1. Okay, now see, for 1 the value was 0 1, for minus 1 the value is minus 1. So this is actually 2's complement binary value, using the 2's complement. So how we can recheck? Again, you can assign the power 2 raised to power 0. Okay, this is 1, and 2 raised to power, here I told you, so it was 1, this was 2. Okay, so you have to assign negative 2 power over here. Why? Because the answer is in negative. Okay, so minus 2 plus 1 is equals to minus 1. So it is proved that this 1 is actually the representation of minus 1. Okay, so next was, you have to represent 0, and by the way these D are representing the decimal. Okay, so minus 0, so I'm not going to solve it because there is no representation of 0 minus 0 in 2's complement. Okay, okay, question number 3 is that a file contains binary coding the following are the 2 successive bytes in a file. This is byte 1, this is byte number 2. One possible for information store is that the 2 bytes together represent one signed integer binary number. If they are asking you 2 bytes together will represent one unsigned integer, right? So what you have to do, give the binary number corresponding to this, showing your working. So actually we have 2 different bytes, but the final answer will be actually representing one single unsigned integer. So what we can do, that let me solve here. Question number 3, you have been given 2 separate bytes. First one is 1011 000 and 1, and the second one was 00 111 00 and 1. Okay, so I'm just marking a line over here so that you can recognize this byte 1, byte 2. Okay, because you have to represent this using, you know, one, you have to represent using these 2 bytes, only one single answer. You need one single answer. So what you're gonna do is that you have to assign them power of 2 raised to power 0, starting from 2 raised to power 0. Okay, so it is 2 raised to power 0 is 1, then 2, then 4, then 8, then 16, and I cannot write properly because I'm using my mouse. 16, then this is 32. Okay, this is 64, 128. So I'm just ignoring them, just we can cross out. We have to, you know, we have to count this power. Like when I am saying we're giving them power, I have to consider the power, but I'm not going to add them. Okay, so this was 32, 64, 128, so this will be 256. Okay, so similarly this will be 512, 124, and so on. Okay, so when you end up after giving all this value, so this is not the value, this is a question 3 and the bracket over here. So when you end up, this is basically the answer final that you will get after adding this value will be 4, 5, 3, 6, 9, and you have represented by 10 because you have to give it the answer in the dendy. Okay, so for this value the one I calculated was 4096, so I can write over here, just keep on adding the values with 1. Okay, so this one is, I guess, 8192, this one is 8192, 819 and 2, and this one, the last one, sorry, this is actually 2. Let me rewrite, this one is 8192 and the last one is 32768. Okay, 32768 and 8. So you have to add these values, so you will get this answer. Okay, okay, now what you are supposed to do in the next question, you have to find out the hexadecimal number for whatever answer you got in the last part. So this was my dendy number. Now I'm supposed to convert into hexa. So what I will do, simply I will write my number like this and I will divide it by 16. Why? Because I am supposed to convert into hexadecimal. So 16 times, by the way, I have already calculated these values, so I am using this. For this you should have a good maths. Okay, so remainder will be 9, and 16 times 177, and then we get the remainder 3, and similarly we get 16 times 16 into 11 times 176, and remainder is 1. So now this cannot be divided any further because 11 is smaller than 16. So finally we got 11, 1, 3 and 9. So what we will do, instead of 11 we will write its equivalent value, that is b, 1, 3 and 9, and this is our hexadecimal number. Okay, so next question is, give one advantage of using hexadecimal representation. Okay, so listen, look here, this was my binary number. Okay, it was taking how many bits? 16 bits. Okay, 2 bytes or 16 bits, and this is my hexadecimal number. You can see the difference, the number of bits used to represent this binary number and the number of bits used to represent this number. Okay, or this number. Now see, when I'm using these values instead of binary number, they are taking less storage space. So what can we do? We can write here that hexadecimal takes less space to represent digits as compared to binary digits, right? Okay, next question is identify the least significant bit and the most significant bit. Okay, so which one is our least significant bit? Remember, here on the right side the last digit is your least significant bit. Okay, you have to represent it with arrow, and here this one is your most significant bit, right? We also call it MSB. Okay, and this is called as LSB, the shorter form. Okay, now next question is computer is using 8-bit number to store a positive and a negative number. What is the largest and smallest possible value it can store using the formulas? So for this, we will start from the smallest possible number. So the range for representing is minus 2 raised to power n minus 1 to what can be represented for the largest possible value. It is 2 raised to power n minus 1 and minus 1. Okay, so this is our formula. This one, the first part represents the value for the smallest possible number, and this second value, this formula represent the largest possible value. Okay, represent, next question, represent minus 7 in sign magnitude and 2's complement. Okay, two parts. Listen, first you have to represent minus 7 using sign magnitude. So in sign magnitude, if you remember, the last digit used to represent the sign of any number that is being represented. Like for minus 7, what is the equivalent value of binary for minus 7? So for let's consider 7. So let's say 7 can be represented using this value. Okay, how? This is 1 2 4 4 5 6 7. So this is actually the value of 7. So we are being given to represent minus 7 using sign magnitude. In sign magnitude, what we will do, we'll just use the last most significant bit to represent the sign of the digit. Okay, so in here we will write 1, and then rest of the values will be same, 1 1 and 1. So here this 1, the most significant bit, is actually representing the negative number. So we can say that the sign magnitude of minus 7 is actually 1 1 1 1 1. Okay, now 2's complement of the same number. Okay, let's consider this value. For 7, I was having, what value was the 7? 7 could be represented by 0 triple 1. Okay, so now I have to use the 2's complement method. So what can I do with the 2's complement method? Suppose this was my positive 7. So for negative 7, using 2's complement, I will invert all the values 0 0 0 1, and I will add last one over here, and what I get, 1 0 0 and 1. Okay, so my final answer over here is 1 0 0 1, right? So see, two values minus 7 can be represented using two different values. This is for sign magnitude, and for 2's complement, this is the value. Okay, now you can also check in 2's complement whether this is accurate or not. How can you do? You can just give the power. 2 raised to power 0 is 1 2 4, and the last will be minus 8. Why? Because this is the 2's complement. Instead of writing positive 8, we will write minus 8. So just ignore this value with 0 and add this value with 1s. So minus 8 plus 1 is equals to, actually it becomes minus 7. I hope it is clear. Okay, next question is signed integer are used in dash form. Signed integers are used in are used stored in dash form. They are stored in any clue. This is 2's complement, right? Okay, 1 in sign magnitude 1 represent, what is the 1 representing over here? I just told you for the sign magnitude over here. The sign magnitude 1 representing the negative value, okay, and whereas 0 represent the positive value, right?